Good afternoon, everyone. Good afternoon, everyone. All the participants are requested to join. Good afternoon, everyone. Good afternoon, sir.
Good afternoon, everyone.
Sir, am I audible?
Yes, madam.
Am I audible, sir?
Yeah, you are audible, madam.
Yeah, sir. Thank you, sir. So, good afternoon, everyone. It's my pleasure to introduce our esteemed resource person, Dr. Gurappa Pattabottula, completed his PhD from NIT Warangal in 2020. His field of study is power systems engineering. In his PhD, he worked on optimal planning of electric vehicle fast charging stations and distributed generators in distribution system. He has total 7 years of experience from teaching and research experience, and he worked as research scholar in the Department of Electrical Engineering in NIT Warangal from 2016 to 2020. He worked as assistant professor in the Department of Electrical and Electronics Engineering, B.V. Raju Institute of Technology, Narsapur from March 2021 to 2023. Currently working as a senior power system consultant in Wipro from 2023 to till date. So his PhD from NIT Warangal, and he has completed his MTech in Power Systems Engineering from Madanapalli Institute of Technology and Sciences, Madanapalli. He did his BTech in Electrical and Electronics Engineering from Annamacharya Institute of Technology and Sciences, Madanapalli, in the year 2009 to 12. Today, he will share insights on impact of electric vehicles on grid and optimal location of EV charging stations. Please join me in welcoming Dr. Gurappa sir. Thank you, sir. Thank you for accepting our invitation. Please go ahead, sir.
Thank you, madam, for your kind introduction. Is my voice is clear?
Yes, sir. Clear, sir.
Just give me a minute. I'm sharing my screen.
Okay.
Is my screen visible?
Yes, sir. Yes, sir.
Yeah. Thank you. Thank you. Today the topic is actually the impact of electric vehicles on distribution systems. Because of there's a lot of impact nowadays on distribution system to minimize the impact on distribution system, especially on transmission system, how we are going to find the optimal location of these charging stations in the distribution systems. That thing we are going to discuss today. Before go to the topic, it is the why nowadays the electric vehicles are more popular. From last uh, few years, Is my voice is audible?
Yes, sir. Audible, sir. It's visible, sir. Your screen also visible.
Yeah, sometimes actually.
Yes, sir. Bandwidth is low, sir. In your
Okay. I will, yes, I will change. Yeah. Um, Nowadays, actually, the people are focusing on more on electric vehicles. Even though there are some the existing electrical corridor or the existing facilities are not supporting the electric vehicles, even though the people are focusing more on the to adopt the electric vehicles. The main reason here is we will wanna discuss one by one. Here, this is the first reason is air pollution. The electric vehicles causes the more air pollution. Because of this, people are focusing more on move into the the internal combustion engine vehicles. These vehicles are causes the more air pollution. The people are focusing on the electric vehicle, the adoption of the electric vehicles. If you see in detail, here it is. Why again it is going to initial page. If you see this, the source of air pollution, if you see nowadays in news also, in Delhi we are seeing these things. The pollution is more in main metropolitan cities. If you take the case study in Delhi, okay, see this is the air pollution in Delhi in percentage.
excuse me,
If you see,
sir. Your
because
screen
of
is not visible, sir. Screen.
not, just give me a minute, ma'am.
Ah,
I hope. Just give me 1 minute. I'm changing.
sure.
Actually, I'm using Teams. This Zoom is new to me. Is it visible? Hello. Now
Yes,
the
sir.
screen is visible. Can anyone
Yes,
please
sir.
confirm?
Visible.
Sorry.
Keep it in full screen, sir. Full mode, full screen.
Yes. Yeah. See here it is. The one of the reason why we are is the air pollution. Air pollution, for example, in Delhi. See here it is. In 1991, most of these vehicles is 53% old. Okay, at the time, because of the industry and domestic is very high. It is 50%. Now, if we go with respect to the time, now if we consider the 2000 and 2001, the air pollution because of the vehicle is 70%. And because of the industry and domestic is drastically reduced. Okay. Can I continue, madam? Is my voice is clear?
Yes, sir. Clear, sir, clear.
Yes, sir.
Yeah, is my voice is clear now? Sorry, I changed the place here. It is some network issues there. Sorry for the disturbance. Is my voice is clear now?
Yes, sir.
Yeah, thank you, thank you. You see here it is. Uh, before going to discuss this thing, what is the impact of electric vehicles and the distribution systems? We will discuss, see why we are going for the electric vehicles, why we are adopting the electric vehicles. Okay, now, if you see this screen here, it is the pollution, the air pollution because of these electric vehicles is very high. If you see, the in 2000 and 2001, according to this data, 72% of the air pollution is causing in Delhi is because of the vehicles. Okay, and if you see in terms of the parameters, if you see here, it is 22. See, more cities in the world, the 22 cities are in the India only. If you consider the total over 30 cities, among the 30 cities, the 22 cities are in India only. Okay. The 41% of nitrogen oxide emissions in Delhi are due to the electric vehicles. And the 23% of particular matters, that is, which size is more than the less than the 2.5 nanometers, is because of this electric vehicles only. Okay, this is the main reason. And also there are some other technical and economic reasons are the, like, we are going to depend upon the some other countries. With that, we are losing the economy of our country. Okay, and also the adoption of the new technologies. There are several reasons. Main is the one thing is air pollution, and the second one is the economy. Okay, if you see, to overcome these things, what our Indian government is doing here is, they launched from 2010. Initially, the Indian government announced a strategy to give the subsidy or to give the reward to the OEMs, that is virtual manufacturing units, that is $950 billion rupees in 2010. Because of this thing, actually, what is happened here, it is within next 2 years, the price of the electric vehicles is come down to the 70%. Okay, with that positive note, again the Indian government has established the own body, that is the National Electric Mobility Mission Plan in 2013, and from there they are concentrating on the improve the electric vehicles, and also to establish the electric vehicle charging station to improve the electrical corridor and to support the new facilities, electric charging facilities. For that one, our government introduced the FAME scheme, that is in 2015. First, they introduced the FAME one. FAME means the faster adoption and manufacturing of electric vehicles. Later, 2019, currently we are in FAME 3. And recently also the Indian government is announced to give the subsidy to establish the new electric vehicle charging station in India. Okay, with this, all the positive notes and the encouragement from the Indian and especially from several state governments, the EV sales are increasing. If you see the sales data, it is increasing, but sometime around 2019 and 2021, the data is the EV sales was somewhat it is decreased due to the this importing of these batteries and some other electronics devices from the other countries during that COVID pandemic period. The EV sales was reduced, but otherwise, from since 2010, the EV sales are continuously increasing. Here it is, and also this small representation is here. It is how much $1 billion is required to establish for the each component of the electric vehicle. Suppose for electric motors, $1.23 billion are required. Okay, and see here in India, these are the key players. Tata Nexon EV. If you see, they are according to the 21 and 22 data, there are 63% share by Tata Nexon EV. Nowadays, if you see any metropolitan cities in India, most of the electric vehicles are Tata Nexon EV. Okay, later it is Tata Tigor and MG. Okay, this is the just to do the overall picture about the what are the different types of electric vehicles and manufacturing companies are there in India. These are the global market players. If you see the globally, the Tesla is the key player. Almost this Tesla and Audi they are going to they are playing the key role in the global market. These are the marketplaces. As we discussed previously, the air pollution is mainly reason. These are the different components in the air pollution. This is the because of this internal combustion engine vehicle. These are the pollutants like particulate matters, COs, and carbon dioxide and nitrogen oxides. This is the general picture I want to give more attention here. It is because of this internal combustion vehicles, that is because of our conventional vehicles, they are releasing this type of the like particulate matters and COs and nitrogen oxides, all these things. Because of these things, our organ system, our complete human system is going to be affected here. It is. This is the just to give the idea about how because of these electric vehicles, the immunity of the system, our human body is going to be degrading. And this is the just air pollution quality, that is the real-time air quality. This is the link for this one to get the live data. What is the real-time air quality index? If you see this thing, 0 to 50, it is the good health. And from 50 to 2, it is moderate. Above 100, it is not good for health. See, here it is to reduce this air pollution, what we can do here it is. We need to adopt the electric vehicles or some other form of the electric vehicles. Here it is. What we need to do here it is, we need to find one of the solution. Go for the low or zero emission vehicles, promotion of the public transport, less depends upon the fossil fuels. Okay. Now, multi benefits to India here it is. If you adopt the electric vehicles, these are the benefits here it is. That is improved air quality, reduced depends upon the imported fuels. Similarly, reduced green GHG. Okay, improved plant load factor for the electric grid. As an electrical engineer, we need to discuss this thing more on the next subsequent slides. What is electric vehicles? Here it is, here it is. Here it is in this electric vehicles, the heart is mainly the battery and the motor, how it is going to be run or how it is going to drive the vehicle. Okay, here we are going to use the rechargeable batteries. What are the challenges with the EV adoption? Okay, see here it is comfort with the why still the few people are not accepting to adopt the electric vehicles. These are the several reasons here it is. They are comfort with the existing systems and resistance to change. The second thing is lack of public awareness. The third one is high vehicles and battery cost. That is high vehicle and battery cost. Okay. Fourth one is limited driving range and long recharge time. Fifth one is lack of charging and stopping stations and import dependence for batteries. Seventh one is managing battery post usage in EVs. Okay, these are the important challenges to adopt the EV here it is. Nowadays, almost the first one is they are completed. Now the people are aware of it. Okay, the second is The second one is also because of this government subsidies and the advantages of EVs. Nowadays, the public is get the more awareness about this thing. Coming to the third and fourth one is high electric vehicle and battery cost. Here it is if you consider the total electric vehicles, 60% of the cost is because of the battery only. Okay. Now, many batteries and many manufacturing units came. The battery cost also going to be come down. Sure. The limited driving range, okay, because of this more advanced battery technologies, they have large energy storage capacity and they can travel, they can move long run for single charge. For example, nowadays this Tesla for one charge it is going around 450 kilometers to 500 kilometers. In Indian on roads also, they are almost it is around 350 kilometers for one charge it is moving. Tata Nexon and some advanced electric vehicles. Coming to the long recharge time, that means to recharge electric vehicles. Always the people or the public is comparing with respect to the conventional one. Suppose if you go to the nearest fuel station, within a couple of minutes, max 5 to 10 minutes, you are going to refill with fuel. Okay, but they are comparing with that with the existing recharge time. But here it is nowadays most advanced EV charging technologies came. You can charge it at your home or you can charge it at your office. You can charge at the public places wherever you want. Okay. There are several subsidies also giving to implement the new charging stations, to erect the new charging stations. Within a couple of years, this challenge also we will mitigate. Okay. And coming to the fifth, this swapping stations still it is not came into our on roads. The swapping station is just like our gas cylinders. Like once the gas cylinder is completed, okay, then we need to book the new cylinders. They will give that new one. Okay. In the similar way, once this battery is discharged, we need to book the new battery. They will replace with the fully charged batteries. The sixth one is yes, still we are depending upon this some battery materials like cathode and anode materials. We are depending on the other countries. This thing, once this battery lifetime is completed, the seventh one is once the battery time is completed, where we need to use or where we need to, what is the next usage of that one? Still, there is a lot of research is going on this thing. Similarly, in the same way, for the solar panels also, after the completion of the lifespan, once it is 20 to 25 years in solar panels, how we need to degrade it, or otherwise how we can convert to into the some other form. Okay, still there is a lot of research is going on in the material science. These are the different fields of engineering. They are working on the electric vehicles. See, if the electric vehicles actually, here as electrical engineers, we need to focus on the main on what is the working on motors, what are the different types of the motors, how we can do the quality control, testing of the battery packs and developing of the optimal battery pack and the wiring and harnessing systems. Here it is, and the different charging methods. Okay, but apart from this thing, actually nowadays because of the advanced artificial intelligence technology like machine learning and deep learning, we need to work on this area also. Like suppose, for example, if you take the battery management system, in the battery management systems, we need to charge the battery or discharge the battery for some hundreds of time. You can get the data and see the data. Okay, by analyzing the data, you can find where the maximum temperature is there inside of that battery. If you see in news, there are news like the electric vehicle is blasted. Okay, the like EV scooters or EV buses are fired. The main reason is here it is, few companies, they are not using the standard BMS, that is battery management system. This standard that is called as in technical it is called as a smart BMS. If we use the smart BMS, that type of things will not come into picture. Here, as an electrical engineer, we need to play the key role here it is. Okay, some people already actually, some all other engineering departments, they are working in the relevant area. Okay, as a electrical engineer, not only we need to focus on the motors and this charging converters. Okay, we need to focus on the how we need to maintain or how to develop the good battery management systems. Actually, it is the very important area currently. Okay, we can use different AI techniques and how to improve the BMS. Nowadays, see, this is the sequence in electric vehicles. Battery is the heart. For that heart, the BMS is giving the oxygen. Okay, as an electrical engineer, if you build the good BMS, then the electric vehicle is the bright future. This is the history of electric vehicles from 1832. These slides just I want to showcase here it is. What are the different types of electric vehicles? Yeah, here this thing. Battery electric vehicles, it is purely powered by the battery. Okay. Then hybrid electric vehicles. In hybrid electric vehicles, if you see, there is a liquid fuel and fuel cell. Okay. And this is the ultra capacitors and ultra flywheels. In battery electric vehicles, only where it is powered by the battery. How this power flow and the mechanical movement is there. Okay. Now see here it is what the power sources but the battery for the hybrid electric vehicles. That is the addition of the battery, internal combustion engine, either it may be petrol or diesel or fuel cell or capacitor, that is ultra capacitor, and flywheel. These are the different hybrid electric vehicles. This is based on the degree of hybridization, that is micro hybrid and mild hybrid and full hybrid. These are the about all this hybrid electric vehicles. This is plug-in electric vehicles. These are the different components. Now this is the battery electric vehicles. Now see here it is. Here it is pure electric vehicles. It is completely free from emissions. Now the source is only battery. It is rechargeable. Okay. As an electrical engineer, now we need to focus on this thing. Which type of motor, okay, we need to use for the better performance, and which type of battery pack and which type of battery technology. Okay, and what is the BMS of the systems? What is the charging converter of the system? What is the charging rate of the system? Okay, these things we need to concentrate here. I will go to the topic here. It is the brief introduction of the electric vehicles before going to the actual topic. Okay, now see here it is. Madam, is my voice is clear? Connect.
Sir, your voice is clear, but, sir.
Yeah,
Okay, sir.
Yes. Yeah, I'm sending this. Yeah, up to now, see, just we recognize what we discussed from last 10 to 20 minutes. See why we are adopting the electric vehicles. Okay, what are the different types of the electric vehicles? Okay, in India, uh, how the Indian or state government is supporting to improve the electric vehicles population. Okay, that is the short description that we discussed. Okay, now we will go in detail about this electric vehicle. Yeah, see, if you see this thing, the improvements in battery technology. Previously, I discussed what are the challenges in EV adoption is. One of the adoption is battery cost. Main important one is the battery cost is more, and also the distance for one charge is less. Now, see, if you see these things, because of the advanced battery technologies like lithium ion, okay, now this energy density is 400 watt hours per kg. Previous the lithium ion, this technology it is 250 watt hour per kg. That means in 1 kg of battery, we can store maximum 250 watt hours. Okay, with the advanced technologies, this lithium ion battery energy capacity, energy density is increased. Now, for one charge of electric vehicle, we can travel for the long time. And similarly, the charging technologies also increase a lot. Okay, if you see there are different types of the charging technologies. That is level 1 and level 2, and if you go to the fast charging stations, charging, that is DC fast charging. Okay, if you use the level 1 charging for to travel 2 to 5 miles, or okay, you need to charge for 1 hour. That means approximately, let us to travel 5 kilometers, you need to charge for again 1 hour there. Now, if you see the advanced electric vehicle charging technologies like Charmico, it is made by Japan. That is the DC fast charging. You can travel. This is the whole data. If you can travel 250 to 300 miles in 20 hours. 20 minutes of charge. Just you can charge for 20 minutes. You can travel to 250 to 300 miles. Okay, there is a quick charging stations and charging infrastructures are existing. Why actually why these people, the public is not, again they are thinking about this energy density means they are always comparing with the conventional fuel. If you take the gasoline, okay, or petrol, diesel, the energy density is 12,000, but the lithium ion energy density is just 400. That means 1 kg of gasoline is having 12,000 watt hour of energy. Okay, now see here the people are actually they are comparing with this one. Now, because of this advanced technologies and battery technologies and charging technologies, okay, the energy density and the charging time is reduced a lot. And also the drastic change in price of EV. Okay, now see this is the gasoline electric vehicles. Suppose, for example, if you see the first table, total cost of the electric vehicle, gasoline vehicle, that is internal combustion engine vehicle. Okay, if you take this is the $50K, that means $50,000. Okay, in EVs in 2000, in EVs in 20,000 is $65,000 of the same capacity and same range. Okay, now in 2000, by 2030, it is almost, currently we reached this target. The total cost is reduced to $19,000. We see from $65,000 to $19,000, the cost of the electric vehicle is reduced because of this advanced battery storage technologies. Similarly, in case of the motors, also there are different advanced motors are there in the market right now. Okay, there the weight by power ratio is also drastically increased. Generally, if you see this thing for the propulsion engine or motor, they are mainly focusing on this parameter. What is the weight by power? Okay, this weight by power is now it is almost equal to the IC engine. Because of this advanced PMSM motors and PLDC motor, the weight by ratio is further it is reduced. Now, previously we discussed because of the adoption of the electric vehicles, the air pollution is drastically reduced. If you see in the first slides in Delhi, because of this electric vehicles, because of this IC engine vehicles, almost 70% of the air pollution is there. We discussed, if you suppose in Delhi, if all the public completely they adopted the electric vehicles, then almost 70% of the air pollution is reduced. But again here it is why I am concentrating this point here. It is now the people are actually they are thinking if you use the power which is generated from the again non-conventional energy sources like thermal power plant, there is no use of adopting electric vehicles. Okay, the adoption of the electric vehicle is very good. It is most encouraging, and it is currently it is very much important to any organization or individually. Hello, someone is having any? Hello. Yeah, I hope I am clear. My voice is clear. Okay. Now see what this slide is giving this information here. It is the adoption of the electric vehicles is not it's okay. It is acceptable. To charge that electric vehicles from the renewable sources is best. That is the very much important we need to observe here. It is adoption of the electric vehicles. Again, the power is generated from the non-renewable energy sources like thermal power plant. It does not make any sense here. It is. If you see here, it is the normal generating systems. Like for example, if you take the thermal power plant, their efficiency is around 30%. The transmission efficiency is 94%. If you multiply these three things, the outcome each year it is 31%. Okay, now this 31% of energy you need to charge into the electric vehicles. Okay, there the final efficiency is 23% only. It is not at all suggestible. Okay, the first thing is adoption of the electric vehicle is good, and that electric vehicle is charged by the renewable energy sources that is best. That is only the final solution. Okay. This slide is giving the complete overview of the different countries. What is their goal? Okay, by which year they are planning to completely move into the electric vehicles instead of using this IC engine vehicles to move into the electric vehicles. What is their target? What is their plan about this? About that, this slide is giving. As for our Indian government, our government has decided by 2030, all the vehicles on the road, okay, is electric vehicles. This is about short introduction of different countries, how they are promoting the electric vehicle population. Now coming to this actual topic, what is the impact of electric vehicles on distribution systems? How we can minimize that impact on the distribution system? Here it is. Okay, as we discussed previously, there are different types of charging technologies are there. That is level 1, level 2, and level 3. Level 3 is the DC fast charging station. The fourth one here, it is the battery swapping station technology. Okay. In this study, we are considering only the DC fast charging station. It's, if you see this power is around 350 kilowatts at the 480 volts. These are the different papers I will suggest to go through this one to get into more idea about this optimal planning of charging stations. Here it is, actually they are mainly focusing on the optimal planning of the electric vehicles. Electric charging stations, okay, and they are mainly considering the power losses and the voltage profile. Okay, here it is, what we need to consider here it is, to find the optimal location of the charging station in the distribution system, we need to consider the simultaneous planning of both charging station and distribution generations only. Suppose, for example, today the EV charging station is planned at some place. Let us take at Vizag, 400 kV substation or some level of distribution system. They are planning to install the new charging station. Okay. Now, at the same time, on the other side, there are some distribution generating people also. They are going to add the generation to the existing electrical corridor. Okay. We need to consider the planning of that charging station. Sorry, the planning of the distributed energy sources also. Why? Because today, if you consider only the planning of the charging stations, if you not consider the distributed generations, that point, it is not going to give the optimal solution. Okay, that is the reason here it is, to find the optimal location of the charging station in the distribution system, we need to consider the existing renewable distributed energy sources and also the energy sources which are going to be connect to the existing electrical corridor. That is the reason here it is. Yeah, that is the reason here it is. I'm considering this study, that the simultaneous optimal planning of electric vehicle fast charging stations and distributed generating systems in the distributed generators in the distribution systems. Here, my main highlight point is here it is. We need to focus on the both the things, not only the just the optimal planning of the electric vehicle fast charging station. It is not going to give the solution. Right now, we discussed just few slides back. We discussed that one. The charging of the electric vehicles from the power generated by the thermal power plant, it cannot make any sense. We adopted the electric vehicles. The main reason is to reduce the air pollution. If you charge the electric vehicles, that is the power generated by the thermal power plants, it does not make sense. Here it is. That is the reason here it is. We need to do the optimal planning of the both the things. Nowadays, the distribution generation are playing like anything. Like suppose, for example, our college itself is a distributed generation. If we are having the rooftop solar power plant, there are many organizations, many homes, many privates. They're having their own solar power plants. They are connected to the grid with the PPPI method. Okay. Here it is. We need to consider that generating systems also. That is, here it is. What I consider here it is. We need to simultaneously consider both the charging stations and distributed generators. For that one, what I did here it is. This is the just a study case. In the let us consider this is the area, a zone. This zone is divided into the this area is divided into the 3 zones like Z1 and Z2 and Z3. Okay. Now, in 3 zones, there are different number of the electric vehicles are there. To find the electric optimal location and size of the electric charging station in these 3 zones, we need to consider these parameters. What is that? Is the charging station development cost. That means in each charging stations, there are number of connectors are there, like 1 charger or 2 chargers or 3 chargers. Okay, and what is the charge for each connector based upon their rating. Okay, we need to consider that cost and the cost of specific energy consumption of the EVs. This point is very important. That is the cost of specific energy consumption of EVs. Suppose, for example, let us consider we all are there. That is our college is there in zone Z3. Okay. Now this optimal with this method, the optimal location it is giving in Z1. Okay. Let us consider our college. We all are there in Z3. We all are having the electric vehicles. Now we conducted the study in this area. Otherwise, take the practical consideration. Let us take the entire Vizag take it as one region. It is divided into the 3 zones like Z1 and Z2, Z3. Okay, our college is there in the Z3. Now, because of the optimal plan study, they decided to conduct the charging station in Z1. That is in other zone. Now, what is this cost of specific energy consumption means? The people or the electric vehicle users who are there in the Z3 region, they have to travel to the Z1 region where the electric charging station is there. That means to travel from Z3 region to Z1 region, there is some energy consumption is there. Okay, that energy consumption also we need to consider. I hope you understand this thing. This fast charging station development cost is easy. It is straightforward. It is always depends upon the number of connectors you are having. There is no other question on that one. The cost of specific energy consumption is this is the variable point, like our network power loss. That means power losses in the systems and voltage deviation in the systems. Okay, these are the one of the variable parameter here it is. Now, see, if you understood these 3 parameters, that is fast charging station development cost, cost of specific energy consumption, and this power loss cost, everything I converted into the cost here it is for the better analysis. And the DC power generation cost, Why? Because suppose, for example, we all are there on the Z3. Okay, all the we are all are there at the Z3 location or Z3 zone. Charging station is there in Z1. Okay, suppose in Z1 we are having some distributed generation, or in Z2 we are having some distribution generator. Okay, there we need to consider the what is the generation cost for that one. Okay, that one also we need to consider here. These are the parameters. First one is that is charging station development cost, specific energy of the consumption of EVs. That means to recharge that electric vehicles, the EV user has to move from their homes to the nearest charging station or from their locations to the nearest charging station. That thing also we need to consider here it is. Okay. Similarly, we need to consider this network power loss and voltage, this power generation cost, that is distributed power generation cost. This is the station development cost. It is straightforward. What is the initial cost here? It is about that. What is initial cost of the system, and this is the connector cost. It is always PC is the capacity of the connector. It is always depends upon this thing. Okay, the capacity of this charging station is always depends upon the number of connectors we are having. S of I is the number of connectors. Okay, the rate of the arrival rate of EVs to I fast charging station. Why? Because we need to calculate this arrival rate. Suppose, for example, in this petrol bunks are there. Initially, they are having 1 point only. Okay. Now, actually, they are planning to improve the number of points. How they are going to improve? How they are going to increase means blindly they cannot increase to the 4 or 5, or they cannot become based upon the arrival rate. How many vehicles are coming to this filling station in each hour? What is the maximum peak demand and what is the less demand in which hour it is there? Okay, what is the nearest fuel station? That all the parameters they will consider. Here also, to fix the number of connectors in the charging stations, we need to consider what is the arrival rate of EVs. Okay. Generally, actually for this one, we consider the data from the practical data. Suppose, for example, in any city, to give the permission to the 6-lane road or 4-lane road or flyover, they will consider this vehicle flow rate. Actually, practically they are doing this system. Suppose, for example, our state government in Vizag, at particular place, they need the flyover means they cannot live blindly. Maybe some other political reasons also there. Sometimes that can work. But what is the actual solution is, we need to do the field study. We need to arrange some field cameras. Okay, that cameras will count the each and every vehicles. What is the flow rate of the vehicles? For example, 2-wheeler, how many vehicles are going? 4-wheeler, how many vehicles are there? Or heavy vehicles, how many they are going? Every hour, how many vehicles are going or moving on the road? Okay, based upon that field data, if you submit that field data to the central government, then the people they see that data and they can actually they can proceed with the further to improve the existing infrastructure. Okay. Like this here it is, we need to consider this arrival rate of electric vehicles. Okay. Then EV user cost. EV user cost means that is the specific energy consumption of electric EV user. See, if you see, let us consider. Just try to understand this first parameter EVUC of Z, I. That means Z is here, it is the zone, I is the electric vehicles. That means ith electric vehicles to move from their location to zone Z, or to move from zone Z to the nearest charging station, what is the energy consumption it is taking? Since if in Vizag you are having the electric vehicle, to go and charge to the Rajahmundry or Vijayawada, it is not suggestible. Okay, with there, what is happening here is the energy EV user cost is going to be increased here. It is. That is the reason we need to consider to get the nearest charging station. This is the grid loss cost. It is how just it is the difference between what is the cost before and after the connection of the charging station and distributed generation. That losses is converted into the again in cost. This is the distribution power generation cost. It is how many generating units we are having, what is the cost for each unit, and also we consider the operational cost and maintenance cost. Here it is. This is the three cost parameters. What is the total investment, operational cost, and maintenance cost? Here it is, by considering the inflation and interest on that one. This is the voltage deviation. Actually, the voltage deviation is 1 per unit is the we are expecting that thing. The deviation is 1 minus what is the actual voltage of that system. Okay, these are the 5 parameters we are going to consider to find the optimal location of the fast charging station. I hope, am I clear? Hello.
Yes, sir.
Yeah. See, actually here it is this 5 points we need to consider to find the optimal location of the charging station. See, this is the objective function. Here it is. The first one is charging station cost. Okay. The second one is the EV user cost. Third one is the power loss cost. The fourth one is generation cost. And fifth one is the voltage deviation. All are, if you see, these 5 parameters we need to consider to find the optimal location of the charging station. Here it is. Now, these are the constants in the systems. Surely, to find the optimal function of to find the optimal value for this objective function, we need to consider some constraints. Okay. Here, these are the constraints related to the generations and voltages and related to the charging stations. These are the areas I consider. Here it is. Okay. It is the case study, the 118 bus systems. Okay. This red rhombus color is there now. These are the feasible places for to construct the charging station or to establish the charging stations. Feasible places in the sense based upon the road and electrical corridor connections. Okay, this all red rhombus colors is the feasible places. These are the EV population data. That means the entire area is divided into this 180 zones. The total area, study area here it is considered is 180 zones. In each zone, this many areas are, this many electric vehicles are there. In practical also, we can get this data by because while we are buying the electric vehicles, okay, it is registered with the PIN code number or some address. Okay, we can get this practical data also there in Kaggle domain. We can get this type of data. Yes, this is the charging probability of the electric vehicles. If you see this thing, the electric vehicles also based upon their availability, based on their free times, they are going to charge the electric vehicle. That means if you see that 5th hour,
it is the 24-hour time span. The 5th hour, it is approximately 0.07. Okay, and it is going to be slightly reducing, and it will be low at the 8th hour. Again, it is going to be increasing. It is 0.1. This probability actually, this is also a practical data. How we are going to get this practical data means, in existing developed countries, if you take this Canada, and there are having the plenty of the Tesla charging stations. In their charging stations, they are recording the data. Suppose, for example, in each hour, how much of electric vehicles are coming, and again that entire 24-hour span, they are converting into this probability. Okay, this is the parameters we need to consider here. It is the total number of electric vehicles, okay, number of available charging stations, what is the initial cost of this, and also we need to consider the land rental cost, all this thing here it is. This is the conventional load power, not the charging station. The conventional, this below waveform is there now. This below graph is showing the average daily load profile. That is the conventional load. What is the load at each hour in different seasons like winter, spring, and summer? Okay, in different season, this is the average load profile. Now, to solve the above objective functions, in this case, I used it, here it is, NSGA algorithm, non-dominated sorting genetic algorithm. Okay, now here it is. Here it is. We need to initialize the population. Okay, there it is randomly going to initialize the population. In the first iteration, it is going to calculate the objective function. Okay, then from that first iteration, the next population will come like this. See, here it is up to this population size is 100, number of iterations is 400. This crossover probability and mutation, these are the things here. These two parameters are very important while you are working with the NSGA algorithm. Okay, now in this study, I considered the 3 different scenarios. What is optimal planning of just charging stations? I'm not considering any distributed generation stations. The second scenario is just optimal planning of the distribution generators. Here, what I am trying to convey here it is, if any system study, when you are doing it, if you consider the only charging station, how it is going to affect the system. That means how the charging station location and size of the charging station is going to impact. Okay. The second thing is just only you consider the distributed generators. Okay, with the previous charging station load. Already the charging station load you connected to the electrical corridor. For that existing charging station load, now you are considering the optimal planning of the distributed generators. Again, the size and location of the generator. Okay. The third case is, instead of doing it separately, if you do this simultaneously, what will happen? We need to see here. Okay. Now, see, if you see the optimal planning of charging stations, okay, only if you consider the charging stations, the number of optimal charging stations is 6, the first waveform, and also so the second figure it is showing. The second figure it is showing the number of connectors in each charging stations. Number of connectors means number of the charging points. Okay. This is the variation of the network voltage and power losses. This optimal Pareto, friends. This is the variation of these 3 parameters, that is specific user, PV user cost, voltage deviation, and network power loss. Okay, this is the optimal location that means charging station 1 is located at the bus number 61. Initially, I shown one diagram with feasible charging stations. The second charging station is at the 108 bus. If you see, the number of dedicated electric vehicles for first charging station is 61. Like this, here it is. We are getting the data. Why we are concentrating on the number of EVs dedicated to fast charging station means based upon this EV, the arrival rate of electric vehicles only, we are going to decide the number of connectors or number of charging points in the charging station. Okay, this is the network voltage profile during 24 hours with and without fast charging station. Okay, if we consider the fast charging station load, the voltage profile is if you see it is too low. The maximum voltage deviation is 0.1.6. That is around it is 0.89. It is not acceptable. Okay, and also if you see this, it is automatically if the voltage deviation is more, then the network power loss is also will be very high. If second scenario is already we connected the charging station to the existing electrical corridor. Now we are planning for the optimal generation scheduling. Again, here it is. We are considering what is the optimal number of generating stations and what is the size of it. Optimal number is 4 and its location is, these are the bus locations 37, 42 and 74, and the size is, this is DC power in megawatts. Okay, with this the grid loss, that is the network loss, is drastically reduced. Okay, now these are the various parameters. Here it is, we need to consider the, yes, if you consider the previous charging stations, this is the voltage profile. Okay, the voltage profile is drastically improved. The maximum voltage deviation is, it is just 0.07. Further, if you do the simultaneous planning, that is scenario 3. If you do the simultaneous planning, there is a lot of reduction in the network voltage and power losses. See, here it is. This is the scenario 3. I am comparing this thing. Here it is. If you see, the network power loss cost and specific user cost is drastically reduced, and that is the required distributed generation also is reduced. Okay, see, if you see, the third scenario is very much important. Here it is. Here my conclusion is here. Suppose if the government or if any individual is planning to is having the goal to establish the new charging stations, okay, in a particular city, they need to concentrate on the what are the new distributed generations like solar and wind in that connected to that system. That means connected to that electrical system. Okay, we need to consider that thing also. Okay, we need to do the simultaneous planning for the both charging stations and the renewable energy sources. This is the main considerations. How it is going to impact the results is explained right now. Okay, I hope, am I clear up to now? Hello.
Yes, sir, it is clear.
Yeah, here it is. Actually, up to now, we are focusing on this optimal planning. What is the impact of charging station on the distribution systems? Okay, to reduce that impact, surely we cannot eliminate. We cannot eliminate. To reduce that impact, how we are going to do the system studies. Okay, finally, if coming to our electrical point of view, here we are doing the load flow as a system study. For any electrical system, the load flow is the basic study we need to perform to go further action or to take further action. The next one is here it is. Now see, suppose for example, today we are planning for the to find the optimal location and size of the charging stations in Vizag. Let us consider today out of 100% of the electric vehicles, let us consider for understanding, let us consider 20% of out of 100, only 20% vehicles are electric vehicles today, right now today. Okay, now we are planning to establish charging stations at various places in Vizag. What we need to consider these things to the present EV population. If you consider the present EV population, to find the optimal location and size is cannot make the sense. Why? Because if you see the EV population data, it is increasing drastically. Today it is 20% in Vizag. Tomorrow, after 1 year, it may be a 25% or 30%. That is the reason before going to do this study, okay, we need to do some forecasting of EV population. Okay, in last 5 or last 10 years, how the EV population is increased in Vizag? What are the factors are affecting? How these factors are directly affecting on the EV population? Okay, and based upon that factors, in next coming years, whether it may be 2 years or 5 years, and we need to do it different scenarios. Next 3 years, what is the EV population? Next 5 years, next 10 years, how the EV population is going to be increased? Why? Because today, if you install the charging station at one particular place, tomorrow it may not be optimal location for that one. Okay, that is the reason we need to do the forecasting of EV population, that is electric vehicles, in which area, how it is increasing flow. Generally, for the practical analysis, how it is doing it is, again, we need to fix the cameras, that is the sensors and cameras in a particular places. Okay, just first identify the vehicles, whether it is the electric vehicle or conventional vehicles. Don't consider it is, okay. Identify the number of electric vehicles or count the number of electric vehicles. Okay, take the data. Today, out of 100, 20% of electric vehicles. Take the total electric vehicles in last 10 or 20 years. Apply the machine learning methods. Okay, do the forecasting in next 2 years, next 5 years, next 15 years, what is happening? Why? Because today it is 20%. Okay, tomorrow it may be a 30% of total vehicles. Okay, tomorrow it may be a 35 or 40% of electric vehicle. With that overall forecasting, we need to do some analysis. Okay, today if you consider the today present population, it cannot make sense. Why? Because future EV population, for the future, the current optimal location may not be optimal. The current optimal size may not be optimal size. Okay, that is the reason in second case, what we are going to do here, we are going to do the forecasting of the electric vehicles. Okay, here it is actually the key point for this one is how the vehicles on the road are increasing and what is the percentage of electric vehicles on the total electric vehicles. I consider here it is the objective function is same. We are not at all going to change the objective function. Here also 5 parameters are there. The thing is here it is what we need to do. We need to consider the future EV population demand. Okay, that thing here it has considered. The objective function what we formulated in previous, that is same. Constraints are same. Okay, the constraints with respect to the charging station is going to be changed. Previously,
the number of connectors at that particular place is depends upon the arrival rate of the electric vehicles. But here it is going to be changed. It is also depends upon the future EV population. Okay, that is the point here we need to keep in mind. This is about just this is about just same objective function what we discussed previously. To solve that objective function here, I use a different algorithm, but that is Shuffle-Frog leaf and TLB algorithm, teaching learning based algorithm. Actually, the combination, the application of this algorithm is depends upon the particular problem, right? Because it is like a humans. Some person may be good in some area, the other person may be good in some other area. Okay, if both of can work combinedly, they can do the better work in that area. Okay, now here the same motto here it is. The Shuffle-Frog lake algorithm is good in exploration. The teaching learning based algorithm is good in exploitation. Like in general terminology, local search and global search. Okay, the first one is good in local search. The second one is good in global search. If we combine this thing, we can get the optimal solution for that one. With that idea, with that one, I used this hybridization algorithm to find the optimal solution for that objective function. This is about the flowchart about that algorithm. It is the detailed steps. Here it is what are the strengths and weakness, why we are combining these two things. Again, here also I consider the three different scenarios. That is, see here it is, the FCS is fast charging stations and DGs is the distributed generations. Okay, FCS and DGs are DG locations are fixed. Okay, the optimal number of connectors in FCS and size of DGs has been determined. In first scenario, the location and charging station location and distribution generation locations are fixed. In previous study I did not. That locations I consider, and I am trying to find the optimal number of connectors and size of DC by considering the future EV population demand. The future EV population demand, I consider it as a four cases. That is the present. If the population is increased to 10%, 20%, and 30%. Okay. What is the second scenario is half of the FCS and DG locations are fixed. The third scenario is completely all the DG locations and this charging station locations are different. Why this all the analysis are considered means, see, in the present, if you take the practical situations, already in the field there are some charging stations are there. We cannot change the charging stations. It is some places it is very difficult. Like in Hyderabad, in Gachibowli, if the algorithm is giving the optimal location to plant the optimal location at the Gachibowli metro station, it is very difficult to get the place there. Okay, that is the reason some other places the location is already fixed. Okay, we need to find the optimal number of connectors. That is the reason by considering the different analysis, pros and cons. Finally, we identified the three scenarios. In first scenario, the locations are fixed. Only we are concentrating on the number of connectors and size of the DC. Second scenario, Few places it is possible to change the location. Okay, that is considered here. It is the third scenario is it is the completely new one. It is the, let us consider the for the particular area they don't have any charging stations. Currently they are planning to establish the charging stations. Okay, for that one, this scenario 3 is suitable. Here again, I connected the, I calculated the optimal number of charging stations and optimal number of DCs. Okay. Here it is going to calculate the, with respect to this algorithm, actually it is calculated for the number of iterations. If you take the 2, the number of generators are 2, it will do the calculations. That means it will do the load flow 400 times, 400 iterations. And it is for 5, again it do the same process. For 6, it is doing the same process. There are multiple calculations here we conducted. And finally, we identified these are the number of charging stations and distributed generators, this one. Number of charging stations is 6 and number of distribution generators are 4. These are the variation of the different parameters in multi-objective optimization methods. These are the variation of the parameters, optimal parameters in each scenario. Directly, these values cannot make sense for you. What is the conclusion here? It is the while you are planning for the optimal location and size of the charging station and distribution generators, you need to consider the future EV population also. If you consider the present EV population, it cannot make sense. Okay, we need to consider the future EV population demand and future EV conventional load demand also. Okay, if you consider this future EV population and future conventional load demand also, it is going to be better optimal solution for the systems. With respect to the both point of view, with respect to the electrical system operator point of view and with respect to the EV user point of view, that is the optimal solution. Now we find the optimal location and size of charging station. Here it is to find the impact of charging station EV load with the different EV modeling systems. Next, I'm going to explain the thing different EV modeling. Again, the same objective function, if you see, previously you seen the objective function has having 5 parameters. That is the same objective function. What is the different here? It is the EV load modeling. How we are going to model this EV load, either using ZIP, that is constant impedance, current and power load model. Okay, this is the ZIP load model. This equation is ZIP EV load model. V is the actual load voltage. V0 is the nominal voltage. Actually, that is the 1 per unit. Then from that one, this ZP, IP, and PP constants are associated with the parameters. Actually, these parameters are there in the existing standards. The second one is exponential load models. Okay, see, this is the exponential indices. Third one is constant current load model. Okay, here it is how the variation of the distribution system parameters are going to be changed
with the different load models. Again, the EVUC index, in the sense that is the EV user cost. The second equation, it is giving them clearly more informations, number of zones and number of connectors. This is the power loss. That is the difference between with and without EV loads. This is the voltage profile index. Actually, why I consider this all as the index means of all these three parameters. If you see these three parameters, if I go to the objective function, I think voltage profile index. This is apparent performance, power performance index. Okay, if you see this all these parameters, all the parameters are within the range of 0 to 1 only. While we are doing the optimizations, the range of that variables. Now this 4 are variables, here it is. Okay, this all are should be in the same range. If we suppose consider if you one variable in one range, the other variable in some other different range, the solution is cannot optimal. Now to calculate the all the parameters in the same range, here I calculated the indexes like power loss index, voltage index, that is voltage profile index, and apparent power index. This is the objective function, here it is. The optimization of these 4 parameters. The first one is EV user cost index, power loss index, second one, voltage profile index, and the fourth one is apparent power index. Okay, these are the again constraints we need to consider, here it is. So while we are solving this objective function, these are the parameters we are going to consider, here it is. This is the test systems. In this test systems, this red color numerical values are the number of EVs in that area. This is the electrical systems. The below one is the geographical area. That means this electrical systems, this 38 bus system is imposed on the geographical area. Same, it is the charging probability of electric vehicles. This is the parameters of EVs and charging stations. Now to find the performance of that any algorithms, actually previously I used the non-terminated sorting algorithm and this shuffle frog and teaching learning base and the hybridization of the two things. To find the performance of that each algorithms, we need to consider these parameters, actually these metrics. Suppose for example, if you use the 3-4 any algorithms, to find which algorithm is giving the better results or something, we can use this metrics, that is convergence metric. That means this metric evaluates the focus towards the optimal Pareto plans. How that particular algorithms is giving optimal values towards the optimal Pareto plan. The second one is space metric. It is evaluating the spread of solution for the optimal Pareto plan. That means the distance between each value from its made value. Okay. This is the the SOC of the electric vehicle also here it is considered. Suppose for example, while we are modeling the EV load, we need to consider what is the SOC of that EV. That means suppose for example, the EV is with the let us consider the present EV SOC is, that is state of charge is 80%. Now, no need to charge it. Suppose the SOC of the EV is 20%. It needs to be charged for the 80%. Similarly, if the SOC of EV is 50%, again it needs to be charged into the 50%. In practically 100% we cannot charge. There is some upper limit. General for understanding, I'm telling these things. Okay, that is the reason we need to consider the initial SOC of the EV also. These are the performance metrics for different algorithms. That means when we compared with the SFL-TLBO and SFL algorithm. That means if you compare the two algorithms, the first box metric is the first box, the average metric here it is. It is comparing the SFL-TLBO and SFL algorithm. The second one is it is different here it is. Okay, like this it is going to compare the values with the different algorithms. This is the average matrix. If S is equal to 0 means all the solutions in the Pareto print are equally spaced, then that solution is actually, that is the good solution, optimal solution. Now, to perform the study on this particular case, I consider the two scenarios. That is, the conventional load is modeled as the constant power load, and the EV load is with the different load models. The second scenario, the conventional load is modeled as the residential, industrial, and commercial. That is RAC load model. Few loads are residential, few loads are industrial and commercial. And the EV load is with the different load models. Different load models means, as we discussed previously, constant power, ZIP, and exponential. Okay, in scenario 1, we'll see, that is the conventional load is modeled as the constant power, and EV load is modeled with the different load models. That means here case 1 means, case 1 here it is the EV load model is the constant power again. This is the, for this case, this is the variation of the network power loss, maximum voltage deviation, and EV user cost. From this optimal Pareto point, not only here it is, in any algorithm, if you are using the multi-objective optimization, from that optimal front, the compromised solution can be determined by using min-max method. This is the maximum percentage of load in each hour during that case, case 1 and scenario 1. You see, this is the objective parameters, case 1, case 2, case 3, case 4. Case 1 is the EV load and conventional load both are modeled as a constant power. Case 2 is ZIP. Case 3 is exponential model. Case 4 is constant model, constant current model. Like this, these are the parameters here it is. If you see this case 2 is giving the optimized values here it is. As compared to this thing here it is. Case 2 is here it is. If you see previously, case 2 is in scenario 1, case 2 in the sense the load, conventional load is modeled as a constant power, and this EV load is modeled as a ZIP load model. Okay, in scenario 1, EV load is modeled as a ZIP model. In that case, it is giving the optimal results. And during that case, these are the maximum power flow. That is, the power is flowing in that particular line with respect to the line MVA limit. And these are the different indexes. That is power loss index, voltage profile index, AV user cost index, and apparent power performance index. Okay, if you see in all the cases, this particular case 2 is giving the better and optimal results. Scenario 2 is the conventional load is modeled as a RIC load model and EV load with the different load models. Here also, if you see this case 2, again the conventional load is RIC load model and EV load is with the ZIP load model. Here it is giving the better results. This is the maximum percentage of load on each hour. First figure. The second figure is the power flow in each line. It is the 38 bus systems. 37 lines are there. In each line, what is the power flow here? It is compared with the line limits, line MVA limit. If you see the power flows, all the power flows are within the limits. These are the parameters for all 4 cases in scenario 2. Okay, here it is. The conclusion from this study is here it is. The first conclusion is to solve any objective function, we can use the multiple algorithms, maybe more than 2 algorithms. To find which algorithm is giving the better solutions, we can use this symmetric and space matrix. Okay. After that, again, to model the EV load model, the ZIP load model is giving the that is constant impedance, current, and power load model is giving the better results. This is the about EV load modeling in distribution systems. Now, up to now, what we discussed it is regarding to the fast charging station. Now, actually, the people are thinking about suppose at that particular place, the fast charging station is not available. If you go with the level 1, and level 2, it takes more time to charge the electric vehicles. The other way here it is, and also if you go to the level 3, it is the quick charging stations. Always the battery lifetime of the battery depends upon the C rate of the battery. C rate means how much, what is the how much of current you are passing to that battery, okay, to charge that battery. If you charge it quickly, the lifetime of battery is like, for example, in mobile phones, we are having the previously normal chargers, standard chargers, now Type-C charge. If old phones are charged with the Type-C, the lifetime of the battery is going to be reduced. Similarly, if the electric vehicles are continuous, that is technically it is work with the charging station, with the charging level. But if you charge with the higher level, the lifetime of the battery is going to be down. The other solution is the battery swapping station. Means this is actually nowadays it is the big area they are focusing here is. Why? Because this battery swapping station, it is going to help the EV users, EV user point of view, and also it serves the grid regulations also. That means that sometimes this battery swapping station can help to maintain the grid stability also. just like a gas refilling stations. This BSS provides the short charging time, like gas filling station. The UV users actually no need to pay the total initial cost. Now, I hope Tata is initiated this thing actually. Um, the EV owner, electrical vehicle owner, no need to pay the total cost of the battery. Just you need to buy the vehicle. Okay, you can pay it as an installment whenever you are charging. In the charging per unit cost, they are incorporating that value. Just give me 1 minute. Yeah, so if you charge for one time, the total battery cost also they are incorporated in that one. Here it is actually the main advantage is here it is the EV user no need to pay the total cost of the battery at first installment. The second thing is regarding to the battery degradation and battery life, no need to worry about the EV user. And coming to the electrical network operator point of view, if you have large capacity of the battery swapping station, it helps to provide the grid regulations. It helps to enhance the grid stability. Okay, these are the two main advantages. This is the parameters I consider to find the. It is just like a optimal scheduling of the battery swapping stations. How we can optimally schedule the batteries. Here are the parameters: the number of batteries taken from the battery stock, battery charging damage, that is battery degradation cost, and electricity charging cost of the battery. These are the models for that one. Battery charging cost. This is average charging damage of EV batteries. This is the dynamic price change considered. That is TOU, time of unit price. In all the developed countries, the battery, the electric tariff is not same at all the time. Okay, the time per unit is going to be changed with respect to the time. This thing also we need to consider. This is the solve that objective function. That is the minimization of batteries in stock, average daily time of unit price. These are the constraints. These are the test that is battery, 85 kilowatt capacity. This used in the Tesla Model S electric
Sir, voice is not audible, sir.
Oh, sorry, I muted it. This is the
Okay.
variation of the battery. This is the variation of the battery system parameters, that is battery swapping station parameters. This is the comparison of two algorithms, that is hybrid and SFL algorithm. With respect to the two parameters, what is the number of battery stock means? Number of batteries are charging in that particular battery swapping station, and what is the cost of during that charging. Here it is what we discussed previously. It helps to reduce the level of peak demand during the low electricity price. That means it increases the load factor of that systems. Similarly, it helps to improve the battery lifetime of the battery. This is the conclusion from this battery swapping station. The main thing is here it is the summarization here it is. If you want to plan the electric vehicle charging stations, that means to find the optimal location and size of the charging stations, you need to consider the both electric vehicle load. We need to consider both the charging demand and distributed generation capacity. Okay, and also you need to consider the present EV population and future EV population demand and future conventional load demand, that is the increase in future conventional load demand. Okay, that thing. The second thing is you need to concentrate on the while you are performing the impact on EV charging station. That is, while you are calculating the impact of EV charging station and distribution system, you need to properly model the EV load. That means you need to select the particular load model to model that EV load. And also nowadays, the people are more focusing on that battery swapping station. It is actually because of the many advantages. And here it is, we need to, the researchers or any persons who are doing in PhD, they can focus on this battery swapping station technology. And in electrical areas, you can focus on the battery modeling and also battery management systems. Actually, nowadays, in advanced papers, in all the papers, if you use any advanced AI technology or machine learning models or anything, it is the acceptable rate of that particular paper is somewhat high. This is my suggestion from this all my experience. And also coming to this academics point of view, all these things are it is actually we can all the data which I discussed with the EV data or some what I mean, this conventional load data or generation data, all these data sets are available in the Kaggle. You can use for our academics or for our R&D purpose. That is from my side. Thank you, madam.
Okay, sir. Any questions from participants? You can ask any questions. Okay. Dear participants, can you ask any questions? Okay. Thank you, sir. Sir, I hope this message finds you well. I wanted to take a moment to express my heartfelt gratitude for your valuable contribution to our online faculty development program. Your insights and expertise truly enriched the experience for all participants. The topics you covered were not only informative but also inspiring, igniting new ideas and approaches in our teaching practices. Your ability to engage and connect with the audience made a significant impact, and I have received numerous positive feedback from attendees. Thank you once again, sir, for sharing your knowledge and for your dedication to fostering professional growth. We hope to collaborate with you in future programs. Thank you so much, sir. Thank you for accepting our invitation and for your presence.
Yeah,
Thank you.
thank you, ma'am. Thank you, madam. Actually, the people who are working on this area, you can reach me because within this 1 hour, 2 hours, it is not possible to cover all the things. If any one of you are working in the same area, you can reach me. I'm happy to help you.
Sure, sir. Sure. Thank you, sir. Thank you, all participants. We have shared the feedback link in the WhatsApp group. You can fill it. Again, we'll meet tomorrow afternoon at 2 p.m. Thank you once again. Now the participants can leave the meeting. Thank you.